Okay, I'll summarize the rules because I don't feel like reading this. Basically, you have players that are rolling die. When they roll the die, they get a number between, let's say, 1 and 6. If you see a green ladder, you're allowed to take it. You don't have to, but you're allowed to. If you land on this position at the end of your move, you have to go back down, etc., etc. So, pretty simple game. It's a die game, and it's sort of a game of luck, to some degree. There's kind of strategy, I guess, but yeah. Well, it depends. It depends. It depends on, like, if you assume the die has equal probability and then you analyze the board and then you're like, if I go through this path and make the calculate, it's not really a game of, I don't know. I think it's just luck, maybe. Who knows? But regardless, the idea is, in this question, you want to find the smallest number of moves needed to complete the game. So that is starting at 1 and reaching 100. And we want to represent this as a graph problem. So let's start here. If I make a move here, and I have a k-sided die, what's the furthest I can move, assuming no ladders and no snakes? 6, right? Yeah. And from here, what's the furthest I could move? 6, in theory, assuming no ladders and no snakes. So in the question, they say you have a k-sided die. So let's say from any given point in time, I have a k-sided die. So that's one thing. So k-sided die. Another thing is, let's say this dimension is n and this dimension is n. If I need a way of encoding the states of the game into vertices into the graph, so I need to map each possible location that I'm in into a vertex in the graph. So how many vertices should I have? There are 100 different states here. How many vertices should I have? 100, great. So we make like 100, if this is n and this is n, we make n squared vertices. For simplicity, I'll go with 9 if n was 3. So we have n squared vertices, order n squared vertices. If there is a ladder, you have the option of taking the ladder. So anytime there is a ladder, you add an edge between. So let's actually forget the ladders. Let's say this is number 1, 2, 3, 4, 5, 6. If my die roll is 6, starting from position 1, I can go here. If I roll a 2, I go here. If I roll a 3, I go there. 4, 5, 6. So if I roll a 1, I go here. If I roll a 2, I go here. If I roll a 3, I go here. If I roll a 4, I go here. If I roll a 5, I go here. And if I roll, let's just call this number 7. So what this means is, for every vertex, draw order k edges, where k is the size of the die, to the next k consecutive elements. And obviously there's some edge cases, right? When I get to the top left-hand corner of the board, I have nothing else to use. If I'm at position 100, I'm not going any higher than 100, and I'm not getting to 106. So if we repeat this process for each vertex, if we have n squared vertices, and we draw k edges, order k edges for every vertex, so far we're at order n squared k in our graph size. So now, the only thing that's left to add is, as I traverse through the initial input array, if I see that there is a ladder from 3 to 42, then I add an edge from 3 to 42. If I see there's a ladder from 8 to 54, then I add an edge. So add an edge for each ladder. Connecting corresponding squares. So we already said we have roughly n squared vertices. We have order k edges going out of each of them. What is the, in theory, the worst case board? When I say worst case, I mean the largest graph that I could get is if every single outgoing edge from my current node was a ladder. if starting here, I had 6 ladders, here I had 6 ladders, here I had 6 ladders, here I had 6 ladders. In the worst case, because I'm trying to bound the size of the graph, this would become 2k edges going out of each one. In the same way, if I think about, what is this thing called? Snake, yeah, sorry. If I think about the number of snakes that I have, in the worst case, I have snakes going, in terms of the size of the graph, I have snakes going backwards across all n squared elements. And actually what I said before about ladders is wrong. I could have, in worst case, n squared ladders, right? I can actually have a ladder from every element to every other element greater than it. And the same thing with snakes. So let's say then that a bound on the number of edges is not, a bound on the number of edges in the graph was per vertex order k for all of the die rolls that I can make. So 1, 2, 3, 4, 5, 6, 7. K for the die rolls. And then n squared for the number of ladders. And n squared for the number of snakes that I could have. So plus.
But doesn't it say each square can only be used one snake per ladder? You probably go with those one snake per ladder.
What?
Yeah, it does say that.
This is why I should read. Okay, if every snake, that makes our life easier. So then the bound on the number of edges that I have is order k plus 1 now. If every square can only have one snake or ladder going to it, the bound on the number of edges is just the number of die rolls that I can make from a square, 1, 2, 3, 4, 5, 6, up to k, plus 1 for either a snake or ladder. So I still have order k edges. And then I add in an edge from I to j, if there is a snake, or if there is a snake, from I to j. And that's the graph I construct. So the question asks, design an efficient algorithm to compute the smallest number of moves required for the token to reach the last square. So I'm starting with my start vertex here, and my target vertex here. And I have a graph that has edges that I can take, up to k edges, starting from each one of the vertices, and I have all the snakes and ladders in. What search algorithm should I use to find the length of the shortest path from S to T? I heard someone whisper something FF. Okay, DFS is one option. So let's say, yeah.
With the graph, though, how do you differentiate between optionally taking a ladder and the fee required to take a snake? Because that's what it says in the in the problem, is that you must slide down if you land on a snake, but you may move up a ladder.
Yeah.
Joe, on the what is it called? Snakes. You don't draw the edges to the following 6k edges. You only draw the edges.
Yes, correct. So there's an edge case here that he mentioned where if the current vertex that I'm on is a snake, so if, thank you for pointing that out, there's a snake from I to j, or if we wanted to just continue, we could just say remove all other drawn edges. So the constraint that he said is, hey, if I have a snake, the problem says I'm required to take the snake. If I've already drawn 6 more outgoing edges, just delete them, or don't draw them in the first place. So let's say now I have this graph, and I want to find the shortest path from S to T. I heard DFS as one option. So let's say we took a simple case of the game, a 3x3 variant. And let's say after constructing, my graph looks something like this. This is obviously not accurate because I need to have more edges outgoing, but I want to illustrate a point here. There's missing edges, there's snakes, all of that. If I ran DFS starting from vertex S, if I pick optimally, I start at this vertex, I move up to here, I go to this vertex, I move up to here, and I say, hey, my path length is 2. But is DFS required to do that? If I start here, DFS, in the worst case, someone describe the execution path in the worst case DFS could take to get to T. Exactly. So my DFS could say I'm going to go deeper, I'm going to go deeper, I'm going to go deeper, I'm going to go deeper. Right? So that is not the shortest number of moves needed to get from S to T. I need a search algorithm that explores vertices closer to me first. Yeah, breadth first search, right. So how would breadth first search look? I would start here. I would then explore neighbors that are 1 away, and then explore all the neighbors that are 2 away. And then I say, oh, the shortest path is of length 2. So DFS is more helpful when finding longer paths, and breadth first search is more helpful while finding shorter paths. That being said, will vanilla DFS always find the longest path? So let's go back to I said that BFS will help us find the shortest path. If we go back to the same example here, same example, S and T. Let's say I want to find the longest path from S to T. Will DFS always do that? No, because in the worst case, DFS can go like this and actually give us the shortest path. It's not guaranteed to. Because I have multiple outgoing options, DFS doesn't always give me the longest path. So I construct the final graph and I run my BFS search algorithm, starting at vertex 1, n squared, where my source vertex is 1, and my target vertex is n squared. So if I have a graph with v vertices and e edges, this is a simple question. How long does BFS take? I have v vertices and e edges. How long does BFS take? Yeah.
V plus e.
Yeah, it takes order v plus e. Cardinality. And in terms of the input size of my problem, n, how many vertices do I have?
N squared.
I have n squared vertices, good. And how many edges do I have?
Per vertex k plus 1, right?
Yeah, per vertex k plus 1. So k plus 1 per vertex, and I have n squared vertices, so in total.
Into k plus 1.
Right, n squared into k plus 1. So k plus 1 vertices, k plus 1 edges per vertex. So I take big O of this whole thing. And then I get big O of n squared plus n squared k plus 1,
Plus n squared.
which is what?
It's n squared k plus n squared.
Yeah, fine. Whatever. Which is what?
K n squared.
Kn squared, yeah.
In our case, k is also a constant.
K is a constant, but it's also an input parameter into the problem. So if k, let's say you for some reason had n cubed, right? So since k, yeah. It's one of those things where it's like, if it clearly stated, like as an algorithms question, like k is an input into your problem, versus k is just a fixed constant 6. It changes. So there are questions about this. Okay, I will move on then. You're given a list Dn of n words of length k over an alphabet sigma in a language you don't know, although you are told that the words are sorted in lexicographical order. Using Dn, describe an algorithm to efficiently identify the order of symbols in sigma. For example, given the alphabet sigma equals qxz and the dictionary d, your algorithm should return qzx. You may assume D always contains enough information to completely determine the order of the symbols. Hint, use a graph structure. Okay. So, let's start here. Imagine you have a dictionary, an English dictionary. We know what the ordering of letters in English is. It's A is less than B, is less than C, is less than D. In English, we know what the ordering is. And I know that if I look into a dictionary here, I have the word apple, which will appear in my dictionary before the word ball, before cat, before cow, before dog. Okay, I know that this is the correct order of words in the dictionary, and I know how they will appear. What this problem is saying is someone has determined this is no longer the right order. This is not right. Or might not be right. Someone's determined a new order of alphabets in the English language for you. And this new order is a mystery. We don't know what it is. But someone gave us a dictionary. Q, Q, Z, Q, Z, Z. X, Q, Z, X, Q, X. And X, X, X. So, someone gave you this ordering. So, you have, in English right now, we know that this is the ordering of letters in the language, and if we opened a dictionary, we would see words consistent with the order. Someone went in and shuffled up the ordering of letters, but they gave you a dictionary of words, and your goal is to reconstruct what the order of letters should be, given that this is the new dictionary. Does that make sense? Okay, so how do we do this? Well, just looking at these words, we know that Q has to come before X. So Q is less than X. I'm going to use this. And it's kind of obvious. Let's make Q comes before X. Let's say that. What else can we tell? So we look at Q and Q. They're about the same. Q comes before Z. So Q comes before Z. Q comes before X. Okay. We know that Z comes before Z. Q comes before X. We already knew that. We now know, what does this tell us? Does this can we say confidently that Z comes before Q just by looking at this? Why not? Because Q comes before X anyways. Give me an example in English to convince me that this is not the case with our current understood ordering system. I agree with you, but I want to vet it out. Yeah, so if I take the words apple and ball, the first letter of apple is A, the second is B. The second letter is P, and the second letter is A. But we know that A comes before P. So what that means is the first different letter in two consecutive words in the dictionary is what captures the information about the ordering of the letters. So we want to focus on the first difference between two letters in consecutive words. So just going back to the first difference thing, right? We saw QQ, QZ. Once we see that Q comes before Z, this word cannot tell us any other information. Q and X, we see that Q comes before X. Once we see this, Z and Q doesn't tell us anything because by analogy, once we saw the first different letter, P and A, we can't say anything about that. Here we see XX, QQ, and we see ZX. Z is the first differing character in these two words, and now we know that Z comes before X. So what does the question say the correct ordering is? Q, Z, X. And that is represented by this path over here. So what kind of path are we looking for now?
Longest path.
Kind of, yeah, we're looking for a longest path. So let's say we're going with this longest path approach. How do I decide what vertex to start running DFS at? You could start at the source. So am I guaranteed to always have one source in my graph?
Well, you're going to have at least.
I'm going to have When may I not have... Let's take a look at the question. D always contains enough information to completely determine the order of the symbols. So yes, if I had two sources, what would that mean? If I had two, let's put it this way. Let's say I had another letter A, and if I had two sources A, that means that I don't know if A comes before Q or Q comes before A. If I don't know if A comes before Q or Q comes before A, that means that the dictionary didn't contain enough information for me to determine which one comes first, which means it's not a valid problem instance, so I don't need to worry about it. Okay, so we find our source. So is this enough? We find our source and we say, hey, I'm going to run DFS. So in the optimal case, we get the path QZX, which is what we're after. But another outcome of running DFS could be, I start here, and I go to X second, then I come back here, and I visit Z third. Well, now my ordering is QXZ, and that's not the same thing as QZX. So QXZ is what this ordering returns. This is from DFS. But what we want is QZX. So this is not right either. Okay, so how can we, yeah?
Can we do topological sort?
We can do topological sort. What is topological sort?
Where we take the, like Q should be less than Z should be less than X.
Q should be, yes, but how would you describe, yeah, go ahead.
You use the pre and post ordering, and then you keep track of the biggest, the smallest person.
Exactly, so topological sort is nothing but DFS with pre and post order numbering. So yes, you're 100% right, we can use topological sort. So you could just say, run topological sort, obtain the sequence ordering, and get your answer. But if you don't know what topological sort is, and if you know what it is, pay attention anyways. I don't know where I'm going to start running DFS. If I pick my worst case vertex, I start with X. I visit X. Is there any outgoing edges from X? So before visiting it, my timestamp was 1. After visiting it, my timestamp was 2. Pick another vertex. Let's say I pick Z next. Before visiting it, my timestamp is 3. There's no outgoing edges. After visiting it, my timestamp is 4. By analogy, before visiting this, my timestamp is 5. I've already visited all of the neighbors of Q, so my timestamp is 6. So the order that we want is QZX. If we take a look at the post-order numbering, when we do a decreasing post-order numbering, we see that we get 6, 4, 2, which is nothing but QZX, which is the order that we want. But are we convinced this works? Let's try a different ordering and see if the topological sort algorithm is consistent, or if this DFS pre-post ordering number is consistent. So pick a different start vertex. Anyone? Z. Do you want to pick Z? Okay, great. So now before visiting Z, my timestamp is 1. I go and I explore the neighbor of Z, which is X. So my pre-number is 2. I have no more outgoing edges from X, so my post-order numbering is 3. I come back here and it's 4. Then I go here and it's 5 and 6. Again, look at decreasing post-order numbering, 6, 4, 3. And the decreasing post-order numbering order QZX is consistent with before. And lastly, just for the sake of argument, let's start running DFS here. My pre-order numbering is 1. I visit this next. My pre-order numbering is 2. My post-order numbering is 3. My post-order numbering is 4. I now visit, no, this is actually not 4. I now visit this. My pre-order numbering is 4. My post-order numbering is 5. And my post-order numbering is 6. Decrease post-order numbering, 6, 5, 3. No matter where you start, when running DFS from any start vertex and analyzing the sequence of vertices and decreasing post-order number, I get an ordering of the alphabet that's consistent with what's given in the question. So here the answer was Q is less than Z is less than X. Algorithmically, do we see what's going on here? So now let's write up the solution. So make one vertex for each letter. Say hi to your rabbit for me. Make one vertex for each letter. Then, what do we do for every set of consecutive words in the dictionary? So here, here, here. So that's order n. These two, these two, these two. For every set of consecutive words in the dictionary, reset of consecutive words. How am I doing on battery? Good. In the dictionary. We want to maintain two pointers that point to the same corresponding indices in the word. Keep moving the pointers inward until we find the first differing character So let's say I have two words here and here. I start my pointers here. In the worst case, how many comparisons does it take before I get the first differing character? 3, which is in this case k, right? So this inner part, keep moving the pointers inward until we find the first differing character. It takes order k time. And how many pairs of yeah?
When you say inward, it's left to right.
Yeah, yeah. How many pairs of consecutive words are there in my dictionary? N minus 1, roughly, right? I start here, then I compare these two, then I compare these two, then I compare these two. So the loop runs order n times. By the way, at the first difference, I can't spell. Differing character. Draw an edge from I to j. And I didn't define I and j, so we'll define I to be the first differing character of the first word, and j to be the corresponding pointer in the second word. And by first and second, I mean relative ordering. And then finally, after I construct my graph, I run DFS with pre-post order numbering. Return vertices in decreasing post order number. So let's take a look at this. If I have, what is the size of the number of nodes in my graph?
Length of the dictionary.
Not the length of the dictionary, the length of the alphabet. So that's going to be the cardinality of sigma.
Yeah.
Okay, and then for every pair of consecutive words, if n is equal to let's use n to be cardinality of sigma for simplicity. So n is the size of our character set. K is the length of our words. So how long, this takes order n to make all of the vertices. How long does this portion of our code take?
And
Yeah, order nk, because I have n pairs of words and up to k comparisons. So order nk. And then how long does it take to run DFS on a graph with, let's say, if I have a graph with v vertices and e edges, my DFS runtime is order v plus e. How many vertices do I have in this graph? And then how many edges do I have?
Also,
Also n?
No. Or wait, is n the length of the alphabet?
no,
N is the number of characters that I have.
no, it's the number of words you have.
Is that how they defined it?
Yes, d of n of n.
Okay, so then let me fix the notation. Apologies. Delete everything I have about runtime, and we'll just use what's given in the question. Make one vertex for each character, so the size of this takes the size of the character set, one for each character. For every set of consecutive words, this is order n, because they said that the dictionary has n words in it. Keep moving the 2 pointers inward, so the length of each word is k, so this takes order k time. So this whole process in red takes order nk time. So how long, now I said DFS takes order v plus e time. The number of vertices in my graph, we said, is the number of characters. How many edges can I have in total in this graph? Yeah.
I think at most n minus 1 because you get an edge from each pair.
You get an edge from each pair. Is n minus 1 the true bound?
I don't know if it's the true value, right?
You know, yeah, I'm thinking through it as well. Is it possible for us to construct a dictionary in a set of words where I can have more than one outgoing edge? So if we take a look at the worst case here, we take, in English, sorry? Oh yeah, I have more than one outgoing edge. I think we can say, though, it's fair to bound the number of outgoing edges by k, which is the number of characters in our alphabet.
Yeah. Well, at every pair or every letter you could draw an outgoing edge technically.
You could.
I mean, it will be k minus 1, right? Because it won't loop.
Yes.
Yeah. It
won't have any cycles.
Yeah.
So the outgoing, per vertex, the number of outgoing edges is k minus 1 max, or order k. So we can say that the number of edges that we have is order nk. So the size of the edge set is big O of nk. And then we can all agree that the size of my character set is going to be much smaller than n. If I have 3 characters, I need at least 3 words more than 3 words to uniquely determine the ordering. So we can say that this is negligible relative to this. So we can then say the total runtime is big O of nk. You can include the sigma if you want, it doesn't really matter. Yeah?
What about topological sort? Does that?
Yeah, that's O of v plus e.
That's okay.
That's DFS with pre and post order numbering. Yeah. Questions? Okay, we'll move on. How are we doing on time? Let G be an undirected graph. Suppose we start with 2 coins on 2 arbitrarily chosen vertices of G. At every step, each coin must move to an adjacent vertex. Describe and analyze an efficient algorithm to compute the minimum number of steps to reach a configuration where both coins are on the same vertex, or report correctly that no such configuration is reachable. The input to your algorithm consists of a graph G and 2 vertices U and V, which may or may not be distinct. So take a second to digest the question. Not that I care if you actually do, I'm just passing time so I can erase. So the game in this lab is not to try to develop new graph algorithms. It's to try to modify our input graphs or turn our inputs into graphs and then run existing graph algorithms like BFS and DFS and topological sort as oracles. Okay. So ideas. Does anyone have ideas? Yeah.
Well, you basically just have 2 points in your graph that you're seeing what the shortest path is between them.
Okay, so let's start there. So I'm going to draw like a really, really simple graph. Did it say undirected?
Yeah.
Okay, good. So I have 1 coin here, and I have 1 coin here. And in every step, I have one coin here, one coin here. In every step, I need to move both of the coins. And I need to see if it's possible for both of the coins to land on the same point. Yeah. Okay. So I'm just restating the problem. Yeah. So in this case, obviously, I can just move the two coins to land on the same point, and I'm okay. What if my starting point was here and here? So is it possible, on every iteration of my game, I need to move both of the coins. Is it possible for them to land on the same vertex ever?
No.
How? No, I'm curious. I don't know the answer. I'm asking. Yeah, I have to. So this will swap, right? And then if I move this, it'll swap. I don't think there's a way of... You know what? What's the smallest graph you can draw where it's not possible? How many nodes does it have? 2, right? If I just take... And then I draw one here, and then one coin here. I have to keep swapping them, and then I can never end up... So what does that tell us about the path length between the starting points of the two nodes? If the number of edges in between is even, then it may be possible. So the path between here and here is odd. So if I need to move both coins on every step, then no matter how I move these, we're just going to keep alternating. So odd paths are not good. Even paths, it may be possible. So now, I just move both of the coins and they're on the same vertex.
Is G necessarily a connected graph?
No. It doesn't say anything. If G is a disconnected graph, so let me just... Both of the coins are here. Let's say that so both of the coins ended up here. I clear this graph out. It said that the starting point can be the same. So if I put both my coins here, then they're already at the same vertex and there's no work for me to do. So now we see a couple of cases of the problem. Does anyone have any ideas on how we think we should solve it? Yes?
I think we need to figure out if there exists a path of even length between the two coins.
Good. Does there exist an even length path between the two coins?
And if there is, then it's the even path of minimum length.
Right. And it's not, is this question asking for the path length or existence?
Return the minimum number of steps.
Okay, great. So we want the shortest even length path. So now we've narrowed down the problem even more. We know it's only possible if there's an even length path. Odd length paths are not possible. Then we want the shortest even length path between the two vertices if it exists. So shortest even length path if there exists one. So now we've really narrowed down the problem. So which one of our search algorithms was more helpful in finding shortest paths? BFS was more helpful. DFS took a longer, was more helpful and was less helpful in finding shortest paths. So let's say that I draw, my graph like this, and I have a triangle, and I have S and T here. Clearly, if I move both of these coins, I can end up on the same vertex within one move. But if I ran a vanilla BFS starting from S, both of these are equidistant. So we have a problem. Because I don't know which one I'll get to. So the issue with BFS is that there's no way of me searching for the shortest even length path in BFS. I can search for the shortest path between two vertices, but I can't search for the shortest even length path, because if BFS always finds the shortest path and the shortest path ends up being odd, there's no way to remove that from the search space retroactively. So let's start thinking about other possibilities. Let's say I run one BFS here and one BFS starting from here. The tool explore queue will end up intersecting at some point. So maybe that's one way of looking at it. How can we force every path length between S and T to be even in length. So if we want to find the shortest even length path between S and T, what if we constructed a new graph such that all of our path lengths were even? Is it possible to do that? What did we do with, think back to language transformation. What did we do when we wanted, what did we do in questions where we wanted to know if the okay, let's start here. Every time I make a move, let's say I'm moving one coin at a time. Every time I make a move, my path length alternates between odd and even, correct? In our DFA, NFA language transformation questions, when we wanted to flip every odd bit, what did we do to the set of states in order to keep track of odd and even length bits? We crossed it with a flag, 0, 1, right? So that there's some relation here between the odd and even flip odd bits problem that we pass into NFAs and this sort of odd even alternating nature of path lengths. Yeah.
Something like running BFS and marking it as either or odd based on the stage.
Right. So that would require, I could do something with BFS marking it as even or odd, but that would require modifying the algorithm, right? So if I took Q and crossed it with 0 and 1, when you drew DFAs and NFAs, Q were vertices, right? And then when I crossed it with 0 and 1, I doubled the number of vertices. So let's do the same thing with this graph. Let's make V and cross it with 0 and 1. So let's take our just simple triangle case. And oh no, sorry. Colors. Okay, and my original input graph, by the way, was this. And my starting vertex was here, and my ending vertex was here, and the solution was just moving both S and T on one move to here. So if we want to alternate between even and odd, what did we do in the DFS, in the case of NFAs? Well, we said delta of Q, our set of states was, we had a state Q even and Q odd. Right? We had Q even, Q odd. After we read a character, and let's say we read some character C, we would update our internal state to be something, comma, odd. So we have an edge from an even pointing thing to an odd pointing thing. So by analogy, let's draw edges only between even and odd instances of corresponding vertices where there exists an original edge in the input graph that's given to me. So that will look something like this for this edge. I suck at thinking in 3D. Alright, let's do this, alright. Then we'll go from here to here, and then we'll go from here to here. Is that right? Mm-hmm. Okay, and then for the, oh, I'm being silly. I know there's an easy way for me to not get confused. Prime, B prime, C prime. So now, what am I missing? I'm missing A prime B. What else am I missing? B to C prime, and C prime to A. Okay. And what were my starting and ending vertices? A and C originally, right? So let's put this to be my start vertex and this to be my end vertex. Is there, and this is S comma 0, T comma 0, right? So the bottom ones are all dotted, have the Cartesian product of 0 at the bottom, and the top ones all have Cartesian product with 1. Is there an even length path between S and T now? Yes. how do I find it? I go, I'm going to make a copy, and I'm going to delete irrelevant edges, just so we can, let's focus right now only on purple edges. So I got, the green edges still exist, but if I want to find my path from S to T, shortest even length path from S to T, there it is. And because there is an even length path from S0, T0 to T0, because there is a path from S0 to T0, by alternating layers, I force every path length to be even. Because the path exists, it's possible within 2 steps. So, yes? Now let's test quickly a no instance of the problem. So this is yes. The smallest no instance that we constructed was if the input graphs look something like this, and I have my coins starting here and ending here, and no matter what I do, if I have to move both coins in every step, I keep swapping and I never actually am able to get both individual coins to end up on the same vertex, so this doesn't work. So let's apply our layering algorithm. So we'll take S and T here, S comma 0, T comma 0 here. We'll take S comma 1 and T comma 1 here. And we're going to connect only alternating layers. So vertex, 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 vertex. This one I can do because there's one edge. Is there a path from S0 to T0? Is there a path from S1 to T1? No. So it's not possible. By adding the flag 0, 1 in, I force alternating between even and odd. And by checking for the distance between S0 and T0, I'm forcing the path length to be even. So, does anyone have conceptual questions so far? Okay, so what's my algorithm? My vertex set that I construct is going to be the original vertex set crossed with 0 and 1. So this is step 1. And how long does it... If I make 2 copies of the vertex set, how many vertices do I have?
2.
So order V. 2V, order V. And then I have an edge between S0, A0 and B1 when there's an edge between A and B in my original graph. And when there's an edge between A and B in my original graph, I have an edge between A1 and B0. So for every edge in my original graph, I create 2 new edges in this new graph that I'm creating. So I also have order 2E edges, which is order E edges. So if A, B in original graph, add A0 to B0, B1, sorry, and A1 to B0 in new graph. So this has order 2E, which is order E edges. Then I run BFS starting from S0 to T0 to find shortest path. And we said BFS takes order V plus E, but we'll call this V prime and E prime because we've constructed a new graph. But V prime has double the number of vertices as, in their new graph that we construct, we have double the number of vertices and double the number of edges. So that's order 2V plus 2E, and then that's just order V plus E. Questions? And we are right on time at 1:50.